April 1942, Detroit, Michigan, Chrysler Tank Arsenal. William Knudsen, director of the Office of Production Management, stood on the factory floor watching the first M4 Sherman tank roll off a production line that hadn't existed 6 months earlier. The tank was olive-drab, functional and utterly ordinary, exactly what he wanted. Around him, the massive factory hummed with activity, thousands of workers operating machinery, welding armor plates, installing engines, assembling transmissions. Knudsen had spent his career in automobile manufacturing, rising to president of General Motors before Roosevelt recruited him to mobilize American industry for war. He understood mass production better than perhaps anyone in America. He knew that wars were won not by the most sophisticated weapons, but by the side that could produce adequate weapons in overwhelming quantities. The Sherman tank embodied that philosophy completely. It wasn't the best tank in the world. German tanks had thicker armor and more powerful guns. Soviet tanks were simpler and easier to maintain in harsh conditions. British tanks had better optics and fire control systems. But the Sherman had one decisive advantage. It could be mass-produced in quantities that overwhelmed all opposition through sheer numbers. American factories would eventually build over 49,000 Sherman tanks in various models, more than all German tank production combined during the entire war. Knudsen watched the tank roll toward the testing area and smiled. This was America's secret weapon. Not superior technology, but superior production capacity that could bury enemies under avalanches of adequate equipment produced by workers who had learned to build automobiles and simply applied the same techniques to weapons of war. The story of how American industry built 30,000 Sherman tanks and the infrastructure, training, and innovation required to achieve that staggering output reveals truths about industrial warfare, mass production, and why quantity sometimes has a quality all its own. The crisis. America unprepared for war. When Germany invaded Poland in September 1939, the United States Army ranked 17th in the world in size and capability, smaller than Romania's army, barely larger than Portugal's. The army possessed approximately 300 tanks total, most of them obsolete models from the 1920s. American tank production capacity was essentially zero. No factories were tooled for tank production, no workers were trained, no supply chains existed. The M2 medium tank, America's standard tank in 1940, was a disaster. Thinly armored, equipped with an inadequate 37mm gun, mechanically unreliable, and tactically obsolete before it entered service. The tank had been designed in the 1930s when military budgets were minimal and strategic doctrine emphasized infantry support over armored warfare. The fall of France in June 1940 shocked American military planners into recognition that modern warfare required armored forces in unprecedented quantities. German panzer divisions had conquered France in 6 weeks through coordinated tank operations that bypassed fortifications and disrupted enemy command structures. The lesson was unmistakable. Tanks were now decisive weapons that determined battlefield outcomes. But America had no tank industry, no production capacity, and no experience building armored vehicles in quantity. The automobile industry built cars and trucks, not weapons. Converting automobile production to tank production presented enormous technical and organizational challenges. President Roosevelt announced in May 1940 that America needed to produce 50,000 aircraft per year, a number that seemed absurdly impossible, but that focused industry on achieving unprecedented production targets. Tank production received similar emphasis. Roosevelt demanded thousands of tanks, not hundreds, requiring industrial mobilization on a scale never before attempted. The Army Ordnance Department faced a fundamental problem: how to design a tank that could be mass-produced using automobile manufacturing techniques while being adequate for modern armored warfare. The solution would be the M4 Sherman, a tank designed from the beginning for mass production rather than technical superiority. Designing for production, the Sherman's origins. The M4 Sherman tank was developed in 1941 as a direct response to combat reports from Europe showing that existing American tanks were completely inadequate. The design process was remarkably fast. From initial concept to production model in less than a year, reflecting desperate urgency. The Sherman was designed by a team of Army Ordnance engineers led by William Knudsen, working with automobile industry engineers from General Motors, Chrysler and Ford. The team included men who had spent careers designing automobile production systems and who understood that mass production required design simplicity and standardization. The Sherman's design philosophy was revolutionary. Make it simple enough that automobile factories could build it, reliable enough that minimally trained crews could operate it, and adequate enough to fight enemy tanks on roughly equal terms. Technical superiority was explicitly sacrificed for production volume and mechanical reliability. The Sherman was powered by a Continental R975 radial aircraft engine, chosen not because it was ideal for tanks, but because it was readily available in quantity. Thousands of R975 engines were already being produced for training aircraft, and the production lines could easily increase output. The engine was reliable, produced adequate horsepower, and could be maintained by mechanics with basic training. Alternative power plants were also designed into the Sherman from the beginning. The tank could use various engines depending on what was available. This unprecedented flexibility meant that shortages of any single engine type wouldn't halt production. Sherman tanks were eventually built with at least 5 different engine types: the R975 radial, Ford GAA V8, twin Cadillac V8s, twin GMC diesel engines, and Chrysler multibank engines. The transmission was adapted from commercial truck components. Not ideal for a 30-ton vehicle, but adequate and produced in volume by companies with existing production capacity. The suspension used vertical volute spring suspension, VVSS, a simple, robust system that was easy to manufacture and maintain in field conditions. The armor was welded or cast steel, thick enough to stop most small arms and shell fragments, but not thick enough to reliably stop German anti-tank guns. The relatively thin armor was a conscious trade-off. Thicker armor would have required heavier structural components, more powerful engines, and more complex production processes. The main armament was a 75mm gun, adequate for destroying enemy tanks at typical combat ranges, and excellent for firing high-explosive shells against infantry and fortifications. The 75mm was derived from a proven French gun design and could be produced in quantity by existing artillery manufacturers. The Sherman's hull was designed for simple production, using either welded armor plates or cast steel. Welding allowed the use of flat armor plates that were easier to produce than complex curved castings. Casting allowed faster production once molds were prepared. Both methods produced functionally equivalent tanks, allowing production to continue using whichever method had available capacity. The design emphasized interchangeable parts across all production variants. A Sherman tank built at the Chrysler Tank Arsenal could use spare parts produced for Sherman tanks built at the Fisher Tank Arsenal, Ford Motor Company, or Pacific Car and Foundry. This standardization was crucial for maintaining thousands of tanks in combat across multiple continents. The completed design was approved for production in September 1941, just 3 months before Pearl Harbor brought America into the war. The timing was fortunate. When war came, the design was ready for immediate mass production. Building the factories, industrial mobilization. Building 30,000 Sherman tanks required constructing entirely new factories designed specifically for tank production. The Chrysler Tank Arsenal in Warren, Michigan, became the largest and most productive tank factory in the world. The Arsenal was built in 1940 to 1941 on farmland outside Detroit at a cost of $21 million, equivalent to roughly $400 million today. The main building covered 113 acres under a single roof, making it one of the largest industrial structures in the world. The factory was designed from the ground up for tank production using automobile assembly line principles. Construction was remarkably fast, groundbreaking in September 1940, first tanks rolling off the line in April 1942, less than 18 months from concept to production. The speed reflected wartime urgency and the cooperation between government and industry that mobilized resources at unprecedented scale. The factory floor was organized as a progressive assembly line. Raw materials entered at one end. Completed tanks drove out the other end, with each workstation performing specific tasks in sequence. The system was directly adapted from automobile assembly lines that Ford had pioneered in the 1920s. The production line was approximately 1 mile long. A partially completed tank would move from station to station, with workers adding components at each stop. The progression was carefully choreographed: engines installed at Station 12, transmissions at Station 15, turrets at Station 23, final assembly and testing at Station 40. The factory employed approximately 25,000 workers at peak production, working 3 shifts around the clock, 7 days a week. Most workers were new to manufacturing, recruited from farms, retail jobs, and domestic service. Women comprised approximately 25% of the workforce, performing welding, machining, inspection, and assembly work that had traditionally been male-dominated. Training was accelerated and focused on specific tasks rather than comprehensive skills. A worker might learn to weld one specific seam on the hull rather than learning general welding. This specialization allowed faster training and higher productivity. Workers became extremely efficient at their specific tasks, even without broad expertise. The factory included its own steel foundry, machine shops, testing facilities, and railroad spur lines. Raw steel entered the factory and completed tanks drove out. The entire production process occurred within the single facility. Similar tank arsenals were constructed across America: the Fisher Tank Arsenal in Grand Blanc, Michigan; the Detroit Arsenal, Ford Motor Company's facility at River Rouge; the Pressed Steel Car Company in Pennsylvania; Pacific Car and Foundry in Washington State, and others. Each factory used similar production methods but adapted them to local conditions and available resources. The geographic dispersal served strategic purposes. If enemy bombing had destroyed one facility, others could continue production. The dispersal also reduced transportation costs by locating factories near steel mills, component suppliers, and transportation hubs. The workers, building an army of production. The Sherman tank workforce was predominantly composed of people with no previous manufacturing experience who learned industrial work through abbreviated training programs designed for wartime urgency. Mary Smith, age 23, had worked as a department store clerk in Detroit before the war. In March 1942, she responded to recruitment advertisements offering high wages for defense work. After 1 week of training, she was assigned to the Chrysler Tank Arsenal as a welder on the hull assembly line. Her training consisted of practicing basic welding techniques on scrap metal until instructors deemed her adequate. She wasn't taught welding theory, metallurgy, or complex techniques, just how to make a specific type of weld on a specific seam that joined hull plates. This narrow specialization allowed rapid training while maintaining quality through repetition and inspection. Smith worked 10-hour shifts, 6 days a week, earning approximately $40 weekly, substantially more than her previous retail salary. The pay attracted workers from across the Midwest who moved to Detroit for defense employment. The work was physically demanding and occasionally dangerous. Tank hulls were cramped, hot, and filled with sharp metal edges. Workers suffered burns from welding equipment, cuts from sharp metal, and injuries from heavy machinery. Safety regulations were minimal by modern standards. Workers often lacked adequate protective equipment and worked in conditions that would now be considered unacceptable. But the work carried patriotic meaning that motivated workers beyond financial compensation. Smith later recalled, "We knew our work was directly helping win the war. Every tank we built would carry American soldiers into battle and bring them home safely." That knowledge made the hard work and long hours bearable. We weren't just building tanks, we were building victory. The workforce was remarkably diverse for 1940s America. African Americans comprised approximately 15% of Tank Arsenal workers, facing discrimination in housing and recreation, but finding employment opportunities that had been largely closed to them before the war. The military crisis created labor shortages that forced reluctant acceptance of black workers in industrial jobs. Women faced similar acceptance, born of necessity rather than principle. Rosie the Riveter became the iconic image of women in defense work, but real women like Mary Smith faced workplace harassment, pay discrimination, and skepticism about their capabilities. Yet they proved as capable as male workers at most industrial tasks, changing workplace dynamics in ways that persisted after the war. Worker turnover was high, the demanding conditions, better opportunities elsewhere, and military draft constantly depleted the workforce. Factories conducted continuous recruitment and training to maintain production levels despite losing experienced workers. The United Auto Workers Union negotiated contracts covering Tank Arsenal workers, establishing wages, hours, and working conditions. The union agreed to a no-strike pledge for the war's duration, surrendering its most powerful tool to ensure uninterrupted production. In exchange, management agreed to grievance procedures, seniority systems, and safety improvements. Worker productivity increased dramatically through 1942-1943 as experience accumulated and production techniques improved. In early 1942, the Chrysler Tank Arsenal required approximately 10,000 worker hours to complete one Sherman tank. By late 1943, the time had decreased to approximately 5,000 worker hours through improved efficiency, better tools, and worker experience. The production system, mass-producing complexity. Building a Sherman tank required approximately 8,000 individual parts sourced from over 1,000 different suppliers across America. Coordinating this supply chain required logistical sophistication that rivaled the manufacturing process itself. The Continental R975 engine was built by Continental Motors in Muskegon, Michigan. The company expanded from producing 150 engines monthly in 1941 to over 3,500 monthly by 1943. The expansion required constructing new factory buildings, installing specialized machine tools, training thousands of workers, and establishing quality control systems that ensured every engine met military specifications. The 75mm gun was produced by multiple manufacturers, including Water-Vliet Arsenal, American Car and Foundry, and Baldwin Locomotive Works. Gun production required precision machining to tolerances measured in thousandths of an inch. The barrel had to be perfectly straight and smoothly bored, or accuracy would suffer. The tracks, each tank required 158 individual track links, were produced by American steel foundries and forged by numerous metalworking companies. Track production was bottleneck that limited overall tank production in 1942 until additional capacity was brought online. The transmission, final drive, and suspension components were produced by automotive parts suppliers who adapted existing truck and heavy equipment components for tank use. The modifications were extensive, but built on established manufacturing expertise. The armor plate was rolled by steel mills, including U.S. Steel, Bethlehem Steel, and Republic Steel. Armor plate production required special steel alloys and heat treatment processes that produced hardened steel capable of resisting penetration. The mills expanded armor plate capacity from essentially zero in 1940 to thousands of tons monthly by 1943. The turret casting was produced by specialized foundries with the equipment and expertise to cast large, complex steel shapes. Each turret required approximately 8 tons of molten steel poured into sand molds, then cooled, removed, cleaned, machined, and inspected before installation. Coordinating delivery of all components to final assembly plants required sophisticated logistics. Railroad schedules had to ensure that engines, guns, transmissions, and thousands of other parts arrived at assembly plants in the right quantities at the right times. Material shortages of any single component would halt production of complete tanks. The Army Ordnance Department established production planning offices that tracked component production across hundreds of suppliers, identified bottlenecks, and allocated resources to overcome constraints. The planning required unprecedented cooperation between competing companies who shared production techniques and expertise to maximize total output. Quality control was maintained through inspection at every production stage. Components were inspected at supplier facilities before shipment. Sub-assemblies were inspected during tank assembly. Completed tanks underwent acceptance testing before military delivery. The testing included driving the tank over rough terrain, firing the main gun, operating all mechanical systems, and checking for defects. Tanks that failed testing were returned for repairs and retesting. The failure rate was approximately 5%, remarkably low given the complexity and production speed. Production. Peaks. The numbers. Sherman tank production increased rapidly from 1942 through 1943 as factories reached full capacity and supply chains matured. In 1942, American factories produced approximately 7,500 Sherman tanks. In 1943, production increased to approximately 21,000 tanks. In 1944, production reached approximately 17,000 tanks. In 1945, production decreased to approximately 3,500 tanks as the war neared its end and orders were reduced. Total Sherman production reached approximately 49,234 tanks across all variants and production facilities. The Chrysler Tank Arsenal alone produced over 18,000 Shermans, more than total German production of all tank types during the entire war. At peak production in late 1943, American factories were completing approximately 60 Sherman tanks per day, more than one tank every half hour, every day continuously. The production rate exceeded German tank production by more than 10 to 1. The production achievement becomes even more remarkable when considering that Sherman production was only part of American armored vehicle output. American factories simultaneously produced thousands of M3 Stuart light tanks, M26 Pershing heavy tanks, tank destroyers, armored cars, half-tracks, and other specialized armored vehicles. The United States also supplied Sherman tanks to Allied nations under Lend-Lease. Britain received approximately 17,000 Shermans. The Soviet Union received approximately 4,000 Shermans. Free French, Polish, and other Allied forces received thousands more. Sherman tanks fought on every front where American and Allied forces engaged Axis powers. North Africa, Italy, France, Germany, the Pacific Islands, Burma, and China. The Sherman's presence was ubiquitous because American production capacity made it available in overwhelming quantities. The cost: economic mobilization. Building 30,000 Sherman tanks cost approximately $3 billion in 1940s dollars, equivalent to roughly $50 billion today. The cost included not just the tanks themselves, but the factories, tooling, training, and infrastructure required to produce them. Each Sherman tank cost approximately $60,000 in 1943, roughly equivalent to $1 million today when adjusted for inflation and economic growth. The cost included materials, labor, transportation, testing, and overhead allocated across the production program. The economic mobilization to achieve this production was unprecedented in scale. Government spending on military production increased from approximately 2% of GDP in 1940 to over 40% of GDP in 1943-1944. The federal budget increased from $9 billion in 1940 to over $100 billion in 1945. The production was financed through war bonds, increased taxation, and deficit spending that increased the national debt from $43 billion in 1940 to $260 billion in 1945. The economic burden was distributed across society through rationing, price controls, wage freezes, and material restrictions that ensured military production had priority access to resources. Steel production increased from approximately 60 million tons in 1940 to over 89 million tons in 1944. The increase required constructing new steel mills, expanding existing facilities, working existing mills at maximum capacity, and deferring maintenance that would be required after the war. Aluminum production increased even more dramatically, from approximately 300,000 tons in 1940 to over 1.5 million tons in 1944. The aluminum was used primarily for aircraft production, but some tank components used aluminum to reduce weight. The labor force expanded from approximately 47 million workers in 1940 to over 54 million in 1944, despite 11 million men serving in the military. The expansion came from women entering the workforce in unprecedented numbers, unemployed workers finding defense jobs, and older workers delaying retirement. The industrial mobilization transformed American society. Over 15 million Americans moved to different states for defense work, the largest internal migration in American history. Cities like Detroit, Los Angeles, and Seattle expanded rapidly as workers flooded in for defense jobs. Housing shortages, transportation congestion, and inadequate infrastructure created urban crises that governments struggled to address. Combat reality: the Sherman at war. The Sherman tank's combat performance was mixed, adequate in many situations, inferior in some, but present in overwhelming numbers that compensated for individual shortcomings. The Sherman's 75-meter gun could destroy most German tanks at typical combat ranges of 500 to 1,000 yards. The gun fired armor-piercing rounds that could penetrate 80 mm of armor at 500 yards, sufficient to defeat German Panzer III and Panzer IV tanks that comprised the majority of German armored forces. But the 75mm struggled against heavier German tanks. The Panther and Tiger tanks had frontal armor too thick for the 75mm to penetrate reliably. American tank crews facing these heavy tanks had to maneuver for flank shots where armor was thinner or call for air support and artillery. The Sherman's own armor was vulnerable to German anti-tank guns and tank guns. The frontal armor was approximately 50 mm thick, adequate against small arms and shell fragments, but penetrable by German 75mm and 88mm guns at most combat ranges. Sherman crews developed tactics to compensate for firepower and armor disadvantages. The standard approach was to use numerical superiority, sending 4 or 5 Shermans against one German heavy tank, accepting that several Shermans might be destroyed while the survivors maneuvered for killing shots. The tactics were brutal and costly in American lives, but they worked because America could replace destroyed tanks faster than Germany could replace destroyed Tigers. The Sherman's mechanical reliability was excellent, far superior to German tanks that suffered frequent breakdowns. Shermans could operate for hundreds of miles without major mechanical failures. When repairs were needed, the simple design and interchangeable parts meant that field mechanics could often restore disabled tanks to operation quickly. German tanks were mechanically complex and often unreliable. Tiger and Panther tanks frequently broke down, and repairs required specialized parts and skilled mechanics that were often unavailable in combat conditions. German tank units often lost more tanks to mechanical failure than to enemy action. The Sherman's strategic advantage was that destroyed or damaged tanks could be quickly replaced. American production meant that tank units could be rapidly re-equipped after heavy losses. German tank units that suffered heavy losses often couldn't be refitted because replacement tanks weren't available. The Sherman's greatest weakness was vulnerability to fire when penetrated. The gasoline engine and ammunition storage meant that penetrating hits often caused catastrophic fires that killed crew members. American tank crews grimly nicknamed the Sherman the Ronson after the cigarette lighter advertised as lights every time. The British developed a partial solution by modifying Sherman tanks to carry 17-pounder guns. Significantly more powerful than the 75mm, the Sherman Firefly could engage German heavy tanks on more equal terms. American forces adopted a similar upgrade in late 1944, introducing Sherman tanks with 76mm guns that had better armor penetration. The Sherman's combat record was ultimately successful, not because individual tanks were superior, but because American production made them available in numbers that overwhelmed opposition. When German tank crews destroyed 3 or 4 Shermans, 5 or 6 more appeared to continue the attack. The psychological impact of facing endless American armor was devastating to German morale. The supply chain. Getting tanks to battle. Producing 30,000 tanks was only half the challenge. Transporting them to combat zones across the Atlantic and Pacific required logistical capabilities on equally unprecedented scale. Sherman tanks weighed approximately 30 tons, too heavy for standard railroad freight cars or road transport without special equipment. Moving thousands of tanks from factories to ports required building specialized railroad flat cars with reinforced frames capable of carrying the weight. The journey from factory to front line typically took 2 to 3 months. Completed tanks were driven from assembly plants to railroad loading facilities. They were transported by rail to ports on the East Coast, primarily New York, Philadelphia, and Norfolk, or West Coast for Pacific deployment. At ports, tanks were loaded onto cargo ships using heavy-duty cranes and specialized loading equipment. The Liberty ships that carried most military cargo could carry approximately 30 tanks per vessel. Those specialized landing ships could carry fewer but deliver them directly to invasion beaches. The Atlantic crossing took approximately 2 weeks in convoy. Groups of merchant ships protected by Navy destroyers and escort carriers against German U-boat attacks. Thousands of Sherman tanks were lost to U-boat attacks while crossing the Atlantic, necessitating even higher production to compensate for shipping losses. Upon arrival in Britain, North Africa, or Pacific bases, tanks were unloaded, inspected for shipping damage, tested to ensure they remained operational, and issued to tank units waiting for equipment. The tanks then moved forward to combat zones by rail or ship if distances were long, or under their own power if closer to front lines. Tank units conducted final preparation, including installing additional armor, mounting spare equipment, and making tactical modifications based on combat experience. Maintaining thousands of tanks in combat required massive supplies of spare parts, ammunition, fuel, and replacement crew members. The logistical tail supporting armored operations was enormous. For every tank in combat, dozens of supply trucks, maintenance vehicles, and support personnel were required. Supply dumps near front lines stocked thousands of spare parts, engines, transmissions, tracks, road wheels, weapons, radios, and countless smaller components. When tanks were damaged or suffered mechanical failures, recovery vehicles pulled them back to field maintenance shops, where mechanics worked to restore them to operational status. The spare parts supply chain reached back to America, where factories produced replacement components continuously. The parts were shipped overseas, distributed to supply depots, and issued to maintenance units as needed. The system worked remarkably well. Tank units rarely remained immobile for long periods due to parts shortages. The variance, adaptability, and innovation. The Sherman's basic design proved remarkably adaptable, spawning numerous specialized variants that used the common chassis and production infrastructure for specialized purposes. The M4A3E8 EZ8 was an improved late-war variant with better suspension, wider tracks, and improved mobility. The suspension upgrade, horizontal volute spring suspension, HVSS, provided smoother ride, better cross-country performance, and longer track life. The EZ8 incorporated combat lessons learned from 3 years of fighting. The Sherman Firefly was a British modification mounting a 17-pounder gun that could defeat German heavy tanks reliably. The British adapted approximately 2,000 Shermans with this modification, significantly improving their effectiveness against Tigers and Panthers. The M4A3E2 Jumbo Sherman was an assault tank with dramatically increased armor, up to 180 mm on the frontal hull, making it nearly immune to German anti-tank guns. The increased armor came at the cost of reduced speed and mobility, but Jumbos proved valuable for breakthrough operations. The Sherman dozer was equipped with a bulldozer blade for clearing obstacles, filling craters, and creating defensive positions. Engineer units used Sherman dozers to prepare routes for following units and clear battlefield debris. The Sherman Crab was a mine-clearing variant with a rotating drum carrying chains that beat the ground ahead of the tank, detonating buried mines. The Crab was essential for breaching German minefields in Normandy and later campaigns. The Sherman DD, duplex drive, was an amphibious variant with flotation screens and propellers that allowed it to swim ashore during amphibious landings. Sherman DDs participated in the D-Day landings, though many sank in rough seas before reaching shore. The M32 tank recovery vehicle was a Sherman chassis converted to a recovery vehicle with crane and winch for retrieving disabled tanks. Every tank battalion included recovery vehicles that pulled damaged tanks back to maintenance areas. The M7 Priest was a self-propelled artillery piece using a Sherman chassis mounting a 105mm howitzer. The Priest provided mobile artillery support for armored and infantry units. The M10 and M36 tank destroyers used Sherman chassis with open-topped turrets, mounting 3-inch and 90mm guns respectively. The tank destroyers were designed to ambush enemy tanks rather than engage in direct combat. The diverse variants demonstrated the Sherman design's flexibility and the advantages of standardized production. Specialized vehicles could be created by modifying a proven chassis rather than designing completely new vehicles from scratch. The legacy, industrial warfare lessons. The Sherman tank production program demonstrated principles of industrial warfare that remained relevant for decades after World War II ended. First, Quantity has a quality all its own in industrial warfare. The Sherman wasn't the best tank on the battlefield. German Tigers were better armed and armored. Soviet T-34s were more efficiently designed. British tanks had better optics. But American Shermans were present in numbers that overwhelmed all opposition through sheer quantity. Second, production capacity matters more than individual weapon superiority in sustained warfare. Germany built better tanks, but couldn't build enough of them. America built adequate tanks and produced them in overwhelming numbers. When the war ended, Germany had produced approximately 25,000 tanks total, while America had produced nearly 50,000 Shermans alone, plus thousands of other armored vehicles. Third, reliability and maintainability are as important as firepower and armor in operational effectiveness. Sherman tanks ran reliably, were easy to repair, and used interchangeable parts. German tanks were mechanically complex and frequently broke down. American armored units maintained higher percentages of operational tanks because Shermans were reliable and repairable. Fourth, industrial mobilization requires cooperation between government and private industry. The Sherman program succeeded because government provided funding, priorities, and coordination, while private companies provided manufacturing expertise, management, and production capacity. The partnership between public and private sectors achieved production levels neither could have reached alone. Fifth, worker training and motivation are crucial for sustained production. The tens of thousands of workers who built Sherman tanks had mostly never done manufacturing work before. Rapid training programs and patriotic motivation transformed inexperienced workers into productive contributors to war effort. Sixth, supply chain coordination determines production capacity more than any single bottleneck. Sherman production required coordinating thousands of suppliers producing components from rubber tracks to precision optics. When any single component was unavailable, entire production lines halted. Managing the supply chain was as important as managing the assembly lines. The final accounting, the Chrysler Tank Arsenal and other factories that built 30,000 Sherman tanks, represented American industrial warfare at its finest. The program demonstrated that industrial capacity, mass production techniques, and organizational sophistication were as decisive as tactical brilliance or strategic genius. The Sherman tank production program cost billions of dollars, required millions of workers, consumed vast quantities of resources, and transformed American society through economic mobilization on unprecedented scale. But the program achieved its objective, providing Allied forces with armored vehicles in numbers that overwhelmed Axis opposition through sheer quantity. When American tank crews complained that Shermans were inferior to German Tigers, the response was simple. Yes, but we have 10 Shermans for every Tiger, and we can replace destroyed Shermans faster than Germany can build new Tigers. The factories that built 30,000 Sherman tanks won the war not through technical superiority, but through production capacity that enemies couldn't match. The workers who built those tanks, many of them women, minorities, and people with no previous manufacturing experience, demonstrated that American industrial might was the decisive advantage that no amount of German tactical skill or Japanese fanatical courage could overcome. Inside the factory that built 30,000 Sherman tanks, America found its secret weapon. Not the tank itself, but the industrial system that could produce adequate weapons in overwhelming quantities, sustain that production for years, and continuously improve through experience and innovation. The Sherman tank production program remains one of history's greatest manufacturing achievements, a testament to American industrial capacity, organizational capability, and the power of mass production applied to warfare with ruthless efficiency.